Curing agents and catalysts for epoxy adhesives, aromatic amines, anhydrides, and catalytic systems. Epoxy resins are among the most versatile thermosetting polymers used in structural adhesives, coatings, composites, encapsulants, and electronic materials. Their performance depends strongly on the curing agents or catalysts used to convert the liquid or low molecular weight epoxy oligomer into a cross-linked thermoset network. Curing agents react chemically with epoxy groups, while catalysts initiate polymerization reactions without necessarily becoming part of the polymer network. Through these reactions, the epoxy resin is transformed into a rigid, three-dimensional structure whose thermal, mechanical, and chemical properties depend on both the resin and the curing system. Several classes of curing agents are employed in epoxy systems. Among the most important are amines, both aliphatic and aromatic, acid anhydrides, catalytic hardeners such as tertiary amines or Lewis acids, and sulfur-containing curing agents such as polymercaptans. Each type produces distinctive network structures and therefore different material properties. Aromatic amines, although widely used in composites and casting resins, are less common in adhesive formulations. Acid anhydrides represent another major class of curing agents, particularly for high-temperature or electrical applications. In addition, catalytic curing systems, including tertiary amines, boron trifluoride complexes, imidazoles, and dicyandiamide, enable homopolymerization of epoxy resins and are widely used in one-component adhesive systems with long shelf life. Polymercaptans and polysulfides provide rapid room temperature curing and are commonly used in fast-setting commercial adhesives. This report examines the chemistry, processing behavior, and performance characteristics of aromatic amines, acid anhydrides, catalytic curing agents, and mercaptan systems used in epoxy adhesive formulations. Aromatic amine curing agents. General characteristics. Aromatic amines are widely used curing agents for epoxy resins because they produce highly cross-linked thermoset networks with excellent thermal stability and strong resistance to chemical attack, particularly by acids. However, their use in adhesive formulations is less common than in composites, molding compounds, and casting systems. Compared with aliphatic amines, aromatic amines offer several important advantages. The primary benefit is their lower reactivity, which results in longer pot life during processing. Additionally, the cured epoxy networks typically exhibit higher glass transition temperatures, improved thermal stability, and superior chemical resistance. Despite these advantages, aromatic amines have several drawbacks that limit their widespread use in adhesives. Most aromatic amines are solids at room temperature and require heating to dissolve or mix with epoxy resins. Elevated processing temperatures may release irritating vapors and increase the risk of skin sensitization or toxicity. Some aromatic amines are also associated with health hazards. For example, certain derivatives such as diaminodiphenylsulfone have been reported to exhibit carcinogenic properties. Another limitation is the dark color of many aromatic amines, which can stain skin, equipment, and substrates during processing. Furthermore, the cured epoxy networks produced with aromatic amines are often relatively brittle. Nevertheless, the relatively low reactivity of aromatic amines can be advantageous in some adhesive systems. Epoxy formulations containing aromatic amines can undergo B staging, in which partial reaction produces a glassy but still fusible intermediate material. These B-staged materials remain stable for extended periods and can later be fully cured by heating. This property enables the production of solid adhesive forms such as powders, films, or dry coatings that function as one-component adhesives with long shelf life. Common aromatic amine curing agents include Meta-Phenylenediamine, MPDA, Methylene Dianiline, MDA, and eutectic mixtures derived from these compounds. Meta-Phenylenediamine, MPDA. Meta-Phenylenediamine is one of the most widely used aromatic amine curing agents for epoxy resins. It is typically an amber to dark-colored solid with a melting point of approximately 65 degrees Celsius. Because it is solid at room temperature, MPDA must usually be heated before being blended with epoxy resin. The compound contains 4 active hydrogen atoms and reacts stoichiometrically with diglycid ether of bisphenol A, DGEBA, epoxy resins at approximately 14.5 parts per 100 resin, ppH. Once dissolved in the epoxy resin, the resulting mixture exhibits good handling characteristics and relatively low viscosity. 3 general procedures are commonly used to mix MPDA with epoxy resins: Both the curing agent and epoxy resin are heated to about 65 degrees Celsius before blending. The epoxy resin is heated to roughly 80 degrees Celsius, and MPDA is gradually dissolved in the hot resin with continuous stirring. Technical grade MPDA may be heated to approximately 80 degrees Celsius and slowly cooled to produce a supercooled liquid that remains stable for several months at room temperature. During mixing operations, MPDA vapors and molten material can stain surrounding surfaces and irritate. After blending with the resin, the mixture has a pot life of about 6 hours at 25 degrees Celsius. If the mixture remains unused beyond the pot life, it gradually undergoes B-staging at room temperature. B-staged MPDA epoxy materials are useful for manufacturing prepregs, filament winding resins, and solid adhesive forms such as films or powders. Full curing typically occurs at 150 to 175 degrees Celsius, after which a post-cure at approximately 175 degrees Celsius is performed to achieve optimal properties. Methylene Dianiline, MDA. Methylene dianiline is another aromatic diamine used as an epoxy curing agent. Like MPDA, it is a solid compound but has a higher melting point, around 90 degrees Celsius. Its low polarity and processing difficulties limit its use in many adhesive formulations. MDA also contains 4 reactive hydrogen atoms. When used with DGEBA epoxy resins, it requires a stoichiometric ratio of approximately 27 to 30 pph. Mixtures of MDA and epoxy resins typically exhibit higher viscosity than comparable MPDA systems. The mixing and curing procedures for MDA are similar to those used with MPDA, although higher temperatures are required due to the higher melting point. Epoxy mixtures containing MDA generally have a longer pot life, about 20 hours, and cure more slowly. MDA epoxy systems also undergo B-staging, allowing them to be processed into solid adhesive forms such as powders or sticks. MDA tends to cause less staining during processing and is often preferred because of its lower cost. However, MPDA generally provides superior thermal and chemical resistance under equivalent curing conditions. Other aromatic amine systems. Aromatic amine eutectics. Eutectic mixtures composed of various aromatic amines are also available as epoxy curing agents. These materials behave similarly to MPDA or MDA in terms of curing chemistry but are liquids at room temperature with viscosities around 2000 cP. Because of their liquid state, they mix readily with liquid epoxy resins without requiring heating. Although these eutectic mixtures may crystallize during storage, they can be easily returned to the liquid state by heating to about 40 degrees Celsius with stirring. This process does not affect their curing behavior or the properties of the final cured epoxy. Solvent solutions of aromatic amines. Aromatic amines dissolved in solvents can sometimes cure epoxy resins at room temperature. The solvent increases molecular mobility, allowing cross-linking reactions to proceed before viscosity becomes too high. These systems typically require cure accelerators to achieve practical curing rates. However, the presence of solvent in the cured polymer lowers the glass transition temperature and reduces thermal resistance. Consequently, the resulting properties resemble those obtained with polyamide curing agents rather than those typical of aromatic amine systems. Diaminodiphenylsulfone, DDS or DADS. Diaminodiphenylsulfone is another aromatic amine widely used in high-temperature epoxy systems. This curing agent is particularly valued for its exceptional thermal stability. DDS melts at approximately 135 degrees Celsius and is used stoichiometrically with DGEBA epoxy resins at about 33.5 pph. Because it is relatively unreactive at lower temperatures, it can be mixed with epoxy resins at elevated temperatures without premature curing. This curing agent produces epoxy networks capable of maintaining mechanical strength at very high temperatures. For example, formulations based on tetrafunctional epoxy resins cured with DDS can retain bond strengths exceeding 1000 psi at 260 degrees Celsius after appropriate curing cycles. Due to its low reactivity, DDS is often used with slight excess concentrations or with accelerators such as boron trifluoride monoethylamine, BF3-MEA. Cure schedules typically involve prolonged heating at high temperatures to achieve optimal properties. Acid anhydride curing agents. Acid anhydrides represent the second most important class of epoxy curing agents after amines. They are commonly used in casting compounds, encapsulants, and reinforced plastics, although their use in adhesive formulations is more limited. Common anhydride curing agents include hexahydrophthalic anhydride, HHPA, phthalic anhydride, PA, nadic methyl anhydride, NMA, pyromolytic dianhydride, PMDA. Anhydrides do not readily react with epoxy groups without the presence of an accelerator such as water, alcohol, tertiary amines, metal salts, or imidazoles. Reaction mechanism of epoxy anhydride cure. The reaction between anhydrides and epoxy groups is complex and involves several simultaneous processes. Ring opening of the anhydride by reaction with a hydroxyl group to form a monoester. Reaction of the resulting carboxylic acid group with an epoxy group to form an ester linkage. Epoxy hydroxyl reactions catalyzed by acidic species, leading to ether linkages. At moderate temperatures, both ester and ether linkages form in comparable proportions. At higher temperatures, ester formation becomes dominant. The balance between these linkages can be influenced by catalysts and reaction conditions. Advantages and limitations. Anhydride curing agents are valued for their relatively low exotherm, long pot life, and excellent thermal properties. They also provide high heat distortion temperatures and good electrical characteristics. However, their relatively slow reactivity and the need for elevated curing temperatures limit their use in many adhesive applications. High curing temperatures can generate internal stresses due to differences in thermal expansion between the adhesive and substrate. Anhydrides are also hygroscopic and readily hydrolyze in the presence of moisture, which can lead to inconsistent curing behavior and reduced thermal resistance. Hexahydrophthalic anhydride, HHPA. Hexahydrophthalic anhydride is a low melting solid with a melting point near 36 degrees Celsius. It becomes liquid at temperatures of about 50 to 60 degrees Celsius, allowing it to be easily blended with heated epoxy resins. When mixed with DGEBA resins, the resulting formulations exhibit low viscosity, long pot life, and minimal exotherm. However, because HHPA is relatively unreactive, accelerators such as benzyl dimethylamine, BDMA, or DMP30 are typically added. HHPA is usually used at 55 to 80 ppH, depending on the resin. A typical curing schedule involves 2 hours at 80 degrees Celsius followed by 1 hour at 200 degrees Celsius, producing epoxy materials with high heat resistance and excellent chemical stability. Nadic methyl anhydride, NMA. Nadic methyl anhydride is one of the most versatile anhydride curing agents. It is a liquid with a viscosity of around 200 cP at room temperature and dissolves readily in epoxy resins. Typical formulations use 60 to 90 ppH NMA with DGEBA epoxy resins. Without catalysts, the mixture may remain workable for months. When accelerators such as DMP30 are added, working life decreases to several days. By adjusting curing conditions and composition, a wide range of mechanical and thermal properties can be achieved. Maximum cross-link density and hardness are obtained using stoichiometric ratios and high-temperature cures. Pyromolytic dianhydride, PMDA. Pyromolytic dianhydride is a highly functional curing agent containing two anhydride groups attached to an aromatic ring. Its compact molecular structure produces extremely high cross-link densities and therefore outstanding thermal and chemical resistance. PMDA-cured epoxy adhesives can exhibit heat distortion temperatures approaching 280 to 290 degrees Celsius. However, PMDA is insoluble in epoxy resins at room temperature and reacts rapidly once dissolved, making processing challenging. Several techniques are used to incorporate PMDA into epoxy formulations, including preparation of glycol adducts, solvent solutions, or suspensions in the resin. These systems are commonly used in high-temperature adhesive films. Catalytic curing systems. Catalytic curing agents differ from conventional hardeners because they initiate homopolymerization of epoxy groups rather than participating directly in the polymer network formation. The resulting polymers typically have polyether structures. Catalysts may be used either alone or as accelerators in conjunction with other curing agents. Typical concentrations range from a few parts per 100 resin. Tertiary amine catalysts. Tertiary amines are among the most widely used catalysts for epoxy polymerization. Common examples include DMP10, tris-dimethylaminomethyl-phenol, DMP30, O-dimethylaminomethyl-phenol, benzyl dimethylamine, BDMA. These compounds can initiate epoxy curing at room temperature, especially when hydroxyl groups are present to enhance catalytic activity. Tertiary amine salts provide latent curing behavior because the amine functionality is temporarily blocked until heating causes dissociation. Boron trifluoride monoethylamine, BF3-MeA. BF3-MeA is a Lewis acid catalyst formed from boron trifluoride and monoethylamine. It behaves as a latent catalyst because the amine moderates the reactivity of the boron trifluoride. Epoxy formulations containing 2 to 4 ppH BF3-MeA can remain stable for months at room temperature. Significant curing activity begins only when temperatures reach 100 to 125 degrees Celsius. After curing, the resulting polymers exhibit dense cross-linking and excellent high-temperature mechanical properties. Imidazole catalysts. Substituted imidazoles such as 2-ethyl-4-methylimidazole, EMI, are widely used as catalysts or accelerators in epoxy formulations. EMI is a viscous liquid with a high boiling point and can cure epoxy resins at relatively low temperatures. These catalysts produce densely cross-linked networks with good adhesion to metals and improved thermal stability compared with tertiary amine catalysts. Latent imidazole catalysts have also been developed for fast-curing adhesive systems. Dicyandiamide, DICY. Dicyandiamide is a solid latent curing agent widely used in one-component epoxy adhesives and film adhesives. It reacts with epoxy groups only at elevated temperatures, typically above 140 degrees Celsius, enabling long storage stability. DICY is typically used at 5 to 7 ppH for liquid epoxies and 3 to 4 ppH for solid resins. Because the material is insoluble at room temperature, it must be finely dispersed, often with particle sizes below 10 micrometers, to ensure consistent curing. Epoxy adhesives containing DICY may remain stable for 6 to 12 months at room temperature but cure rapidly when heated to 145 to 160 degrees Celsius. Polymercaptan and polysulfide curing systems. Polymercaptans and polysulfides are sulfur-containing oligomers with reactive sulfhydry L-SHUSH groups. These groups react readily with epoxy rings to produce cross-linked structures at room temperature. Polymercaptan cured epoxy adhesives are notable for their extremely rapid curing. Some formulations can cure at temperatures as low as 0 degrees Celsius to -20 degrees Celsius, making them attractive for low-temperature applications. Typical systems have pot lives of 2 to 10 minutes and reach handling strength within 10 to 30 minutes. Such systems are widely used in commercial, 5-minute, epoxy adhesives. The curing reaction involves the formation of a mercaptide anion when a tertiary amine catalyst reacts with the mercaptan. This highly nucleophilic species opens the epoxy ring and propagates the reaction through successive steps. Despite their fast curing, polymercaptan systems have disadvantages including strong odor, low heat distortion temperatures, and brittleness under peel stresses. Advances in formulation chemistry have reduced odor and surface skinning problems, but the limited thermal resistance remains inherent to the epoxy mercaptan reaction mechanism. Conclusion: epoxy curing chemistry encompasses a wide variety of mechanisms and curing agents, each providing unique advantages and limitations for adhesive applications. Aromatic amines produce highly cross-linked networks with excellent thermal and chemical resistance but require elevated processing temperatures and may present toxicity concerns. Acid anhydrides offer long pot life, low exotherm, and high heat resistance, though they require catalysts and elevated curing temperatures. Catalytic curing systems such as tertiary amines, boron trifluoride complexes, imidazoles, and dicyandiamide enable homopolymerization of epoxy resins and are particularly useful in one-component adhesive systems with extended shelf life. Finally, polymercaptans provide extremely rapid room temperature curing, making them suitable for quick-setting adhesives despite their limited thermal resistance. Understanding the chemical behavior and processing characteristics of these curing systems allows materials scientists and chemists to tailor epoxy adhesives for a broad range of industrial applications, from low-temperature bonding to high-temperature structural materials.